Thanks for the introduction. Yeah, today I'm going to talk about this interesting phenomena of landscape connectivity. So this is joint work with Rong Ge and Xiang from Duke and also many people here at Princeton. So what is mode connectivity? So this is a phenomena that was very strange to me. So this is, so consider you train a neural network. Let's say you pick different random initializations, so you usually end up at different solutions. Let's say you end up at these two solutions, A and B. Well, once you have these two solutions, you can try different things. One thing you can do is you can try to directly interpolate between these two solutions. And not very surprisingly, so in this picture, the warm colors represent low loss, and the cold colors represent high loss. As you can see, if you directly interpolate between these two solutions, you will cross this region which has really high loss. And that's not very surprising, right? Because usually we think of a local minimum as a well, and it's surrounded by other things that have very high loss. But it turns out empirically people were able to find these paths. In this case, the path from A to C, and then from C to B. And if you follow this path, you actually stay in the region where the loss is very low. So local minima found by gradient descent are actually connected by simple paths. In this case, the simple path is just a path with two line segments in the parameter space. So if you go from A to C and C to B, your loss stays at a very low level. Yeah, so every point on this path is basically another solution of almost the same cost. So this was very surprising to me. Maybe this is already surprising, but let me also explain why I was super surprised about this the first time I learned about it. Part of the reason I was really surprised was I was working on these ideas of trying to show that for many non-convex optimization problems, all local optimal solutions are also globally optimal. And there we have encountered two kinds of symmetry, or two kinds of geometry for the optimization problem. So there's one class of problems where I will call matrix problems. So these are problems where usually you want to just find a low-rank matrix M. So the way you can do that is if I know M is low rank, I can write M as the product of two smaller matrices. Here I worked on, I showed you the simpler case where M is symmetric, so I write M as X times X transpose. So in this case, because the final matrix I want to learn is M, so for many different X, they actually generate equivalent solutions. So more precisely, for any orthonormal matrix R, if I rotate my optimal solution by this orthonormal matrix R, then it gives me the same solution because XX transpose the matrix M is not going to change if I apply this transformation. On the other hand, there's another type of problems which I will call tensor problems, but roughly speaking, these are the problems where you are trying to find K components. So the simplest example you can think of is maybe a clustering problem where you are trying to find, say, K centers for clusters. So here, if I encode these centers as vectors, we will no longer have the rotational symmetry that we have before, but we still have some other symmetry. In particular, I can permute the ordering of these vectors, and because I only care about the set of vectors, this does not change my solution. So this type of problems will have permutation symmetry. And for these two types of problems, I have always thought that all the matrix problems have mostly connected local minimum, right? Because if you think about it, this set of orthonormal matrices is mostly connected. I say mostly because it does have two connected components, one with positive determinant and one with negative determinant. But they are mostly connected. On the other hand, for the problems on the right, then you will usually have isolated local minimum because the set of permutations, we know there's only k factorial number of permutations and they are kind of discrete. So for neural networks, well, we know that they only have permutation symmetry, right? I can permute the neurons, I can rename the neurons, and they are going to output the same function. But I cannot arbitrarily rotate the intermediate layers of neural network. That will not give me the same neural network. So neural networks seem to only have permutation symmetry. So why do they actually have connected local min, which looks like the left picture, right? Question?
Do you mean local minima or global minima?
Yeah, so here I guess the same argument can work for both local and global minima. And in particular, for both of these two types of problems, there are examples where we can show all local minima are global.
No, but I mean for neural networks.
For neural networks, I'm more talking about, let's say, global optimal solutions. Okay, so there actually has been some understanding of this. So a partial answer to that is the reason that neural networks behave like the left picture is because they are highly overparametrized. They have more parameters than you need to actually represent a ground truth neural network. So there are a lot of existing works that tries to explain mode connectivity using overparametrization. So roughly speaking, what they show is if the network has some special structure and is highly overparametrized, then all the local minimum, and in fact, there will not be, then all local minima are also globally optimal and they are connected. Well, at least all the local minima are connected. So, but here, what's important is that they rely on the network to be highly overparametrized. That means the number of neurons needs to be at least as large or even larger than the number of training samples. So the problem with this approach is that neural networks in practice are not as overparametrized as these papers require. But neural networks in practice were also found to have connected local minima. So the problem we are trying to answer here is, can we try to prove similar result in a mildly overparametrized regime? And by mildly overparametrized regime, I vaguely just mean if the number of neurons is smaller than the number of training samples, at the very least. Okay, and what we show is actually you cannot hope to prove this result for all local minima or all global minima. We can actually construct counterexamples that show for neural networks, not all local or global minima are connected, even in the overparametrized, even in the mildly overparametrized setting, as long as your neural network is not highly overparametrized. We can also show a positive result that says solutions that satisfy a property that we will call dropout stability are connected. And it's also possible to switch out this notion of dropout stability with some other notion that were used to prove generalization bounds for neural networks, but we will not get into detail in the talk. So let's first look at the first result. We show that even in a very simple setting, we have a two-layer neural network. And it's so simple that the data xi, yi pairs are actually generated by a ground truth neural network that has only two hidden neurons. So it's a two-layer neural network with two neurons in the intermediate layer, in the hidden layer. Even for the simple example, we consider optimization of a two-layer neural network, but with many more hidden neurons, with h hidden neurons, where h can be any number, and it can be much, much larger than 2. So in this case, there always exists a data set that only has h plus 2 samples, such that the set of global minimizers are not connected. So note that because the data set has h plus 2 samples, which is larger than h, we are in the mildly overparameterized setting. But still, the number of parameters in this neural network is actually still larger than the number of samples, because the number of parameters is h times the input dimension, and input dimension is a large constant. So that shows that we cannot actually hope that all local or all global minima are connected. So we need to ask ourselves, well, why do we still observe that all the local minima found in practice are actually connected, right? So it turns out that it's widely believed that standard optimization algorithms, such as gradient descent, will only find very special local minima. So there are many conjectures about what properties that these local minima will satisfy. And we will actually see a lot of these, I believe, later in the workshop. But in this talk, we will focus on a notion that we call dropout stability. So what is dropout stability? It's very simple. We say a network is epsilon dropout stable if after removing half of the neurons at every layer, and we will, of course, allow you to rescale others appropriately, if by doing this only increase the loss of the network by at most epsilon. So if this is your neural network, then after removing half of the neurons, you get this network, which requires the loss of this middle network to be at most epsilon more than the original neural network. And for technical reasons, we also require you to allow dropout on a subset of layers. So this is, of course, reminiscent to dropout training, where during training, you can randomly throw away half of the neurons. But our assumption here is actually even weaker than that, because we only require there exists a way of pruning away half of the neurons. It doesn't have to be randomly throwing away half of the neurons. So what we are going to show is if we have two neural networks that are both epsilon dropout stable, then we can construct a path between them whose maximum loss is not much larger than the loss of these two endpoints. And the amount of loss here, epsilon, is the same as the parameter in the dropout stable question.
Yes, in zeroing at random, or there is, can choose half of the neurons.
You can choose half of the neurons to drop out. Okay, so at a high level, how do we show such a theorem? So here are the high-level steps. The high-level steps are simple. I have these two neural networks. I want to connect them. Well, I can first connect this network to its dropout version. Similarly, I can also try to connect the bottom network with its dropout version. Now, once we have these two dropout versions, these are networks of size half, right? So I can actually stack them together. And when I do that, these two networks actually never interact with each other. So I can actually do a linear combination or a linear interpolation between them. So the intermediate step is actually simple. So we will actually focus on how to connect a network with its dropout version. So of course, the first idea is maybe you can try direct interpolation. But usually that doesn't work, even for a simple two-layer linear neural network. So this doesn't have any nonlinearities. You can actually write out what happens when you do interpolation. What happens here is you actually have a term that corresponds to the first network, a term that corresponds to the second network. But you also get this intermediate term that correspond to a mixture of the two networks, which, for example, reminiscent of a centaur, which is half human, half horse. And this term is really hard to handle, right? We don't know what it does because it combines parameters from two networks. So in general, linear interpolation should not work and it should have high cost. So instead, we will actually construct a path very carefully. What we rely on is that we can use two types of line segments. So a type A segment is going to say that if two parameters of neural networks both have low loss, and they only differ in the top layer weight, so all the previous layers, these two networks are exactly the same, but their top layer weights are different. So in this case, we can actually always linearly interpolate between them because it's easy to see that the standard neural network architecture is actually convex in terms of the top layer weight. When you have a convex function, you can always do a linear interpolation. But of course, just doing type A move is not going to be enough because the two initial parameters are not going to be the same in all the bottom layers. So to solve that problem, we say that if a group of neurons do not have any outgoing edges, right, if they are not connected to the output, then these are essentially dead neurons. They are not very useful. But because they are not contributing to the output, we can also rewire their incoming edges arbitrarily, and that does not change anything. So if I do this type B move, the output of the network will not change. And of course, no matter how I do that, I can do a linear interpolation. So we will show that just using these two types of steps, we can construct a path from one network to its dropout version. So I will actually show you an example of a path for a 3-layer network. So we are going to try to connect this 3-layer network to its dropout version. So it will have actually 5 steps. So in the first step, we will connect this network with a version where only the first layer is dropped out by half. So this is a type A move because I am only changing the top layer weight from having connections to everything to having connections to half of the neurons. But now, after I do that, in the second step, I notice that the right half of the neurons no longer have any connection to the output, so I can modify its input arbitrarily. And in particular, I actually modify its input to only have connection to the left half of the bottom layer. Notice that, so now the network is basically having this network, but also have a different version of the network here, which has no output. So in the next step, I'm going to swap the output layer from the left half to the right half. Because I have prepared the weights for the right half correctly during the previous step, this network is actually now equivalent to this network, which is just the version of the neural network where 2 layers are dropped out by half. And that's already, and we are mostly done here because after this step, I can just continue to remove all the unnecessary weights that I do not have. So from here, I can remove anything that's connecting to the left part and anything connected to the right part of the bottom layer. And the resulting network is actually equivalent to a neural network, to a dropout version of the original network where half of the neurons are thrown away. So we can, of course, extend this kind of a construction from 3-layer to an arbitrary number of layers by induction. So the result is we will construct a path from one neural network to its dropout version, and the length of the path, or the number of line segments in the path, is going to be proportional to the number of layers. So it is a bit more complex than what you can actually find in practice, which is just a constant number, or actually 2 line segments. So we actually tried to construct these paths for some neural networks that we can actually train. So on the left part, we have an experiment on MNIST dataset where we trained a 3-layer convolutional neural network. So of course, everything I said works for the fully connected networks, but they can be easily adapted to convolutional neural networks. So for MNIST dataset, we just find 2 arbitrary optimal solutions, and we construct the path according to the theorem that I just showed you and the construction that I just showed you. And that actually performed really well. The loss remains low, the accuracy remains high. We tried the same thing for a larger network, which is a VGG11 network on CFAR10. And here the construction is not as good. As you can see at the middle, when you actually reach the dropout version of the network, the loss is significantly higher. But note that this is actually still much lower than what you would get if you do direct interpolation. So direct interpolation will give you a loss that's on the order of 3 or 5, like on the order of constants, so much larger than 0.3 that we have here. Yeah, so in conclusion, what we show here is that for neural networks, if you are not in the highly overparameterized setting, if your number of neurons is smaller than the number of training samples, then you cannot hope to show every global minimum are connected to each other. But if you only focus on special type of local optimal solutions that are robust to dropout or robust to random perturbations, which we didn't cover here. But those solutions will all be connected. There are still many open problems in this direction. So first, the path we find according to the theorem, it consists of number of segments that's linear in the number of layers. And that is still more complicated than the paths found in practice. So in practice, you can fairly easily find paths that have only 2 line segments, or it's just a Basel curve. So basically, the paths found in practice just have 1 additional set of parameters that you need to learn. And there are also settings where paths are known to exist in practice, but even though the solutions are not as dropout stable as we had hoped. In particular, you see that in our CFAR experiment. In particular, what we found is if you apply dropout to the lower layers of the convolutional neural network, then the quality of the solution actually suffers a lot. But if you only apply dropout to the higher layers, the solutions are still very good. And the open problem that I'm more interested in is whether this property of mode connectivity have anything to say to optimization rate. So now that we know all the global optimal solutions are connected, does that mean it is somehow easier to find these global optimal solutions? Thanks.